continue from what we actually learned yesterday. So the few things that we went through yesterday. The first one was what? Yeah, we actually saw how to what's the capacity of program memory and also what is the capacity of data memory, and we saw how to actually derive the range of address. Is that what we saw, right? Then what else we saw yesterday? Yes? Types of instructions we saw. Then we saw how status register actually indicates the particular operation or the status of the CPU. So we actually stopped yesterday at types of operations. Now, as I mentioned earlier, we have two memory. One is program memory and one is data memory. So in the program memory is where we used to store the programs, as I illustrated yesterday, and in the data memory is where you store the data. So which means, yesterday we saw the instruction set. I hope all of you have the instruction set today. We'll be going into more detail into the instruction set tonight. So all these instructions, they perform, remember that in pipelining we learned that there are two stages of instruction, right? One is the instruction fetch, another one is the instruction execution. The instruction fetch is done from the program memory. It fetches the instruction from the program memory. The execution is done at data memory. So in other words, all the instructions that you see in the instruction set, all the execution is done on data memory. Is that clear up to this point? What happened? Okay. So we saw a few types of instruction operation categories. What is the first category? Byte-oriented operation, which means, what is byte-oriented operation? Any instructions that manipulates the whole byte belongs under the byte-oriented operation category. The second one we saw, byte to byte. It's actually moving, copy and pasting from one location to another location. Where is these two locations? All this location is referring to data memory locations. Is that clear? So there is how many instructions for byte to byte? There's only one. So that's why in the instruction set you don't see a specific category for byte to byte, because byte to byte also falls under byte-oriented operations. And then what's the third one? Bit-oriented operations. So bit-oriented operation means the instructions which actually manipulate only the particular bit. So those instructions allows us to manipulate only the bit instead of the whole byte. So those are known as bit-oriented operations. And what's the next? Literal operations. What is literal operation? Literal means value. So we actually saw that how do we actually load a value inside the memory content is by using literal operation. Is that okay? So of course we have control and also the sixth one. The control operation and also the sixth operation we will see in chapter 2, and it will make more sense there rather than seeing now and you can't really relate on how the instruction really works. So what we're going to do now is we're going to go and see the instruction format for each one of this operation category. So the first one, we will see the instruction format for byte-oriented instructions. So byte-oriented instructions has this format. So what do I mean by has this format means? Now one instruction has how many bits? 16 bits. Instruction, I'm talking about instruction. Instruction is 16 bits. How can you know? Actually you can can you all see this? So what we're going to do now is we're going to focus on the first operation, type operation, which is byte-oriented operation. And you see each instruction is 16-bit. Now each one of these 16-bit has a format. This is actually the format. It has this particular format. So let us actually see what this format actually means. So you have 16 bits, right? From bit 0 to bit 7, how many is total? 8 bits. This 8 bits is denoted as F, and then you have the 8 and the 9th bit actually. Can you zoom? It's okay. So the 9th bit, or bit number 8, is actually A, and 9 is actually D, and then from 10 to 15 is actually written as opcode. So what does each one of these mean? We will see in a while. So all these instructions falls under the byte-oriented category, right? And they have this kind of layout, the format. This is the format for this byte-oriented instructions. Now, so for illustration purpose, to show how actually this thing all works, let us actually take this particular instruction. So just to show how this format is like, so we'll take one instruction and we'll take that as an example and we'll expand from there. Is it okay? So this first instruction, what it does is that it adds the content of working register to the content of file register. So this instruction performs addition between these two file registers. So you'll have so this instruction performs, one is working register, the other one is file register. Remember in yesterday's class we told that you will be introduced to two special function registers. One was status register, the other one was working register, right? So today we are going to see working register. Now working register is nothing but like a normal register. Only thing, the only difference is that it has a name. It's given a particular name, is known as working register, or the short form is WREG. So it's working register. Now this working register, if you can see in most of the instruction, the working register is wherever you see the W. This W actually denotes working register. So in most of the instruction, wherever you see W, the working register is actually involved. So later as we do more examples, you will actually know what the actual usage of working register is. So for now, we'll just stick to this, okay? Later you will see why we don't add file register to file register, because there is no instruction to do that. There is only instruction which adds working register to file register. So don't worry about how do we actually how do we know when to use this? Don't worry, we'll see that in tutorial 2 questions. So for now, just want you to understand how to actually fill in all the blanks. Because we have taken this example of an byte oriented operation which has this particular format. So we're going to see how to fill in all the alphabets. So I have drawn the visual graphic for you. This is how, for this subject, I always like to draw so that you can visually see what's actually happening. So this instruction, as I mentioned before, this performs addition at the content of working register to the content of file register. So can you imagine this? Are you all following up to this point? Yes or no? Yes. Okay, fine. So and you have this F, D and A. Now these 3 fields, F field, D field and also A field. We don't have Garfield here. Field. So it's correspond here, D, A, F, F, F. So most likely you know that you need to replace the alphabet. Now do you see this is the opcode, this is the format, right? Does it have the same format? So that's what it means that byte oriented has this arrangement. So the first 6 bits from here to here, this is known as opcode. So what is meant by opcode is that when the CPU actually sees this code 001001, it knows that this code is referring to add working register to file register. Each one of this opcode here is unique. You cannot have a same opcode, otherwise you'll get confused, right? So which means every opcode denotes a particular operation. Do you understand? That is the computer's language. So it understands that. So when it says 001001, it knows that it's supposed to perform add the content of working register to file register. Do you notice how am I reading this instruction? That is how also you should read, and that's how also you should understand. Add the content of working register to file register. Now you can also see the description here. Add working register and F. F refers to file register. So what this opcode, you understand already, right? So what is this F field here? Of course, if you see in your notes, mention that this one is a bit file register address. This one is destination. This one we'll leave for a while now. Later we'll come back to this. So when we add the content of working register to file register, now this working register is a special function register. All the address of special function registers are already known to the CPU. That means the CPU knows the address of working register already. But then you want to add to file register, right? Now this file register, you need to provide the address of the file register. So can you recommend any or suggest any address? Okay, well, this address, when we're talking about this address, am I referring to data memory or program memory? Data. Remember I told you that all the executions are done on data memory. So any file location that we're talking about, it is at data memory. So any address that you want to suggest? Any address? Here I just give one address. Hex 100. Is it okay? Is it a valid address for data memory? Why? Why is it a valid address for data memory? Yes? Do you understand the question? At least say something somewhere. I'm asking is hex 100, is it a valid address for data memory? Why yes, why no? Huh? It's valid because it's 12-bit address. What? Valid, right? It's hex 100 is 12 bit, right?
Yes.
Is it valid or not?
Yes.
Valid, lah. Any doubts on that? Or are you following or not following in first place? So let's say now we want to perform addition between the content of working register to the content of hex 100. So this is the file register. So when you want to add the content of two file registers, of course this is special function register because it has a name. This is GPR, general purpose register. They don't have a name, unfortunately. You address them by address. This one special, but it has a name, so you can refer by the name. So what do I mean by special function register? Why you can refer by name? Because this letter WREG is actually affiliated to the address hex FD8, which is actually the address of working register. So when you tell the microcontroller to add two memory locations content, you need to provide the address of both. Then only the CPU will know where to fetch the first data from and where to fetch the second data from. Are you following? But this instruction adds working register, file register. The address of working register is known or not known? The address of working register, is it known or not known? It is already known to the compiler. I mentioned earlier, all special function registers address are known, which means when we write here WREG, the CPU knows that WREG is referring to hex FD8. Remember the slide? These are all the special function registers, right? All the special function registers, sorry, FE8. Did I say FE8 or FD8? FD8. So FE8. So these are all the special function registers. Actually, these are their respective addresses. But then we don't need to know the address because the name is actually tagged to this address. Like you tag your friend in Facebook, right? So this name is actually tagged to this address. So when we mention working register, the CPU already knows its address, which is hex FE8. Is it okay? Any question up to this point? So when you want to add two, one of the address is already known, right? Which means the working register's address is already known. So now you want to add to another file register, which is F. Now does the microcontroller or the CPU knows the address? No. So we have to provide the address. Where do you provide the address? Here. You need to provide the address here. But then do you notice the problem? So can you follow why we put address here? Do you understand why we need to supply the address here? Okay, when you want to perform addition between two file registers, do you follow up to that point? Where is this two file register located? Data memory, right? Now, until and unless if you don't provide the address of this two file register address, will the CPU know where to get the data from? No, it won't know, right? Because the data are inside the location. Unless it knows the address, how it want to take the content and add? Do you get it? So now, this instruction add WF is actually adding the content of working register and also the content of a file register, any file register. In this case, we have chosen the file register to be hex 100. Now the same thing, when we want to add those two content, we need to provide the address of both. But in this case, because one of the file register is a special function register, it has a name, working register. So, and what did I mention about working register? The working register address is already known. So which means one file register address already known. The other one you don't know, right? The CPU don't know. Because in this instruction, add working register. Yes, I know where is working register. It is actually at hex FE8. And then you say add to file register. So the CPU asks, okay, file register, but which file register? Do you get the point? So for this file register, you have to provide the address. This is already known. So this is the unknown. Wow, sound like known and unknown. So you have to provide the address here. Is it clear? I don't think so I can make it any more clear. If you still have problem understanding, please do ask. For now, any questions on this? Okay? Are you following? So now, since this F field is where we are supposed to provide the address. This is our address, right? Hex 100. So that means here we should write the address hex 100, so that the CPU will know that add the content of working register to file register. Which file register? We provide hex 100. Oh, at hex 100. But then there is a slight problem. What is the problem? This F field only allows 8-bit file register address. This is how many bits? This is how many bits? So there is a mismatch. How? We dropped the subject. So there is a problem here. This F field only allows 8, whereas the address is 12. Now, why the engineers have actually designed such a way? Is that because they want to keep the one instruction length as 16. Now let's take 16. Just now you saw, right, one instruction is 16. If from the 16, if you allow this to be 12 bits, how many more bits left will be there? 4. With 4 bits, how many combinations can you have? 16 lah. So which means, let's say out of 16, if you allocate 12 bits for address only, you will have only remaining 4. With 4, you can have only 16. Then you can only have 16 instructions only. So what the engineers thought, this is the problem. Then you may say, sir, why? Why the hard work? Increase lah, why 16? Make it more, 32, 64. Make it long. Now you should remember, when later on when you become engineer, you all become right. Should be engineer. So whenever, especially whenever you want to design computer hardware architectures or embedded design, we always, or the designers or the programmer, always think about space. If you write the program very long, what will happen to the space? You require more space. You eat up more space. More space on the hardware means more money, because you need to, the chip is supposed to have more space to more higher capacity. So what they decided that, never mind, they are not going to increase. We will keep with the 16. Let one instruction be 16, we want 32, then headache. 16 bits are having so much headache already, never mind. So what they decided, okay, what we do is, instead of giving 12, we only allocate 8 bits. Now what happened when they actually do like this is, it's quite smart actually. Coming back to the chapter of data memory. This is all happening in data memory. Yeah? So data memory, remember, it has a capacity of 4096 bytes, right? With 8-bit, how many possible combinations that you can have? 16. With 8 bits, how many combinations you can have? 2 by the power of 8 is 256. You can have 256 combination. So what they did was, they actually took data memory and they divided it into groups. So, and they named this group as banks. They divided this into banks. So each bank has 256 bytes, which means with 8 bits, if you have 8 bits, how many locations you can access? I see something now. Do you understand what I'm trying to say or ask? With 8 bits can give you how many possibilities? 2 by the power of 6. 256, right? So you get 256. So what they did, they divided into 256 sections. So if I divide by 256, how many banks will I have? 16. We have 16 banks. So each one of these is 256, 256, 256, 256. And each one this segment is known as bank. So this is known as bank 0, bank 1, bank 2 until bank 15, because it starts from 0. Start from bank 15. Okay? So this one has the address 000, right? When it reaches 256, what happens? 00 to F5 is 256, right? Yes or no? Yes. So you already right, really sure, yes lah. After 0 F5 is what? Yes. It's actually 1, 0, 0. Then it will increase until 1 FF. After 1 FF is 200, it will go until 2 FF. Likewise, the bank 15 will be F00, dot dot dot. Here will be F, F, F. You following? Sorry about that, I have to take the call because this is my brother ordering food, so I have to take the call. I missed the food. So, each one of these is divided into 256, 256, 256, 256. You can see the pattern, right? Now, you can also notice that the front number. These 2 digits is how many bits? All these are 8 bits, is that right? This number digit is how many bits? 4 bits. Do you notice the front number is same number as the bank? This is 0, right? The bank number also 0. This is 1, the bank number is also 1. This is 2, the bank number is also 2. 15? 15. Is it okay? Can you see this? So, Coming back to this thing, we are still in the same subject matter of adding working register to hex 100. So when you want to write this instruction, you have to write it add the content of working register to file register. This is known, this address is known, this is not known. So what is the address of file register? Remember, the F field only allows us to write the 8-bit value only. Out of this 12-bit, how much is 8-bit? 00 is 8-bit, right? So I can only write here hex 00. Okay? Then you may ask, sister, what happened to the 1? Where's the 1? Don't worry, there is a thing for the 1. We'll come back to the 1 in a while. Okay? So we'll see, we'll leave the D field for a while now. We'll focus now on the A field. Correct, right? See the slide. Okay, we'll skip the D part for now. We'll go to the A. Now this A field here, it actually refers to bank. And this A field gives you two options. Either you can, the one in black ink here is the options that you can actually write here. This is the option that you can write. So there is A, Access Bank, and also bank. Bank is actually using the bank scheme. So we will see what is this bank scheme about. Now remember that because you divide into 256, 256, you created a bank. Now in order for you to select this bank, at one time only one bank can be activated. So there is another special function register which is known as bank select register. There is another special function register which is known as bank select register. This bank select register is a special function register. Take note that any register or file register which has a name is a special function register. So you can see this is bank select register. From the name you know that this is used to select the bank. And it uses, of course all file registers have 8-bit, but it only uses 0, 1, 2, 3, which means 4 bits. It uses 4 bits. Why do you think that we only need 4 bits to select the bank? Yes? The bank? The bank? The bank only has 4 bits. The answer should be, you're coming there. But there are 16 banks and therefore you need 4 bits. The name is bank select register. How many banks you have? In order for you to select 16 locations, how many bits you need? So that's why bank select register only has 4 bits. Okay? Now in order for you to activate the bank, there is one instruction that you need to use to activate the bank. The instruction is, don't worry, later you will see the format. For now you just learn the instruction, it's quite easy. This one. Move literal value to bank. Move LB. Move LB means, and then you're supposed to fill here a value. The value that is supposed to write here is which bank that you want to activate. So that means if you want to activate bank 0, you should write here 0. If you want to activate bank 1, you should write 1. 2 means 2, 15 means 15 decimal or hex F. Is it okay? Now, rewinding back, coming back here. This address belongs in which bank? It is very easy, right? You can see. This belongs in bank 1. So which bank you are supposed to activate? You activate bank 1. So you activate bank 1. So this instruction, I just erased the top one. So before you write this instruction, you need to include another instruction, which is that one. Don't worry about the technicality aspect, just want you to understand how the file register is being added. So you're supposed to include move LB, which bank that you want to activate. This instruction, what it does that, this instruction controls the BSR. This B here, this B is actually referring to BSR. So when you write here 1, it actually loads the value 1 into this register. And whatever value that is loaded into BSR, that bank will be active. So now when you want to read this, and whenever you're using the bank scheme, what is supposed to do? A is referring to the bank scheme, right? I just put a bank scheme. The bank scheme. Of course, you have not learned Access Bank yet. We are using the bank scheme, right? Bank scheme means you are activating any one of the bank. So if you are using the bank scheme, you have to write here bank. So this part here at the A field here, you're supposed to write bank. So when we read this instruction, first it will execute this one, right? Move LB1, what does it do? It activates bank 1. And then you come to this instruction, add the content of working register to the content of file register, which is at address 00. Take note that if you see in terms of 8 bits, there are a lot of 00, right? Here goes 00, here also goes 00, here also goes 00, here also goes 00. But the 00 from which bank? So then it will see, are you using bank scheme? The CPU will check. Are you using bank scheme? Yes. You are using bank scheme. Then it will check which bank? Bank 1. So what happens? 1, 0, 0. So you will have access to this location. So what happens? Here is 8 bits. Here is how many bits? Total is 60. So do you get back the 12-bit address? So this is done by the engineer, so you all should be proud. Maybe in the future you are going to think something like this. So I never think like sir. Just make it long. So do you understand this one? Take note that this field F here only allows 8 bits, so you can only write 8 bits. The remaining 4 bits automatically is used to select the bank. Is it okay? Any question up to this point? Anything that you don't understand? Anything you want me to repeat? Anything you want me to rephrase or explain? Yes.
Just out of curiosity,
Yeah.
from the DS3, there's a colon to 0. There's a ratio to 0.
Not ratio to 0, it's from 0 to 3. Not ratio, it's not ratio, it's showing from bit number 0, 1, 2, 3. That's what it indicates, not the ratio. If you see in MATLAB programming, you have the colon. Colon shows the range. Semicolon is end of the. Yes.
So the CPU register has a certain address.
Yeah.
Can we use the address to address in random?
Come again?
Here we use the hex 100, right?
Here.
Can we use the same as the working register, which is XE8?
Okay. If you want to use F, okay, your friend was asking. Here we already use special register, and here you want to use the special function's address. Can, but in this case, if you use the special function register's address, if you use FE8, it doesn't make any sense, lah. Because you want to add the content of working register back to working register. So it doesn't make sense in that way. But of course, if you want to write the address of the special function register, yes, you can. But again, remember, all the special function registers are in bank 15. So which means the starting will be F. So you need to select the bank 15, which is a tedious work, and we don't do that for a very strong reason you will see later on. It's not a advisable thing, and you will realize that you won't be doing that also. There is no need for you to do that. After this point, you are catching up? So we left with another one more field, right? B, destination. Now this is performing addition. When you perform addition, there will be an answer, right? So you need to choose the destination where you want to load the answer. Now you only have two options. Either the answer you load back into the file register, or you load back into working register. So only have two options. So let's put some values inside here. When we add these two, what's the answer you get? Hex 7A, right? Why is it taking so long for you? Hex 7A, right? Now the hex 7A, remember that this instruction at this moment is only dealing with two file registers. What are those two file registers? That means this instruction at this instruction has access to two file registers. What are those? Working register and what is the address of file register? Hex 100. So therefore, when the CPU or the ALU computes the answer can only be kept in one of these two, because this instruction has access to these two locations only. You can understand? So you can choose either here or here. So wherever you choose, let's say if you choose working register, the old value will be overwritten. So the answer will be 70. Of course, then later we can use byte to byte operation to move the answer from here to another location if we want. But I'm telling you, in terms of the instruction, the destination field, it only allows you to choose between any one of those two. Does it make sense? So the D field there, here, this one. What you can write, you can only write capital F or capital W. So in this case, if I want to load back the answer in working register, I should write here capital W. Take note that the one in green, which I'm going to do now, the one in green is the option that you can write in this particular field. If you even this W, if you write small letter, you'll have error. This and this must be capital. So at this D field, you can only write capital W or capital F. If you write any other character, you'll get error. Same with this A field, you can only write capital A or capital bank. Is it okay? So for this instruction, what's happening now is, add, I just repeat how it works. Add the content of working register to the content of file register. What is the address of file register? Hex 00. Are we using banking scheme? Yes. which bank? Bank 1. So what is the actual address of the 5 register? 100. So after you add, you'll have answer, right? Where do you want to store? Working register. Therefore the answer will be stored here. Can you understand? So that is this byte instruction format. Any question on this? Okay. So, therefore, when you see this diagram, do you see it's actually separated into banks now? Bank 0, bank 1 until bank 15. Do you see this one? The BSR? You use this 4 bit. You can see the 4 bits here. So just now ours was 1, 0, 0. So we actually have access of this. Is it okay? So that's why this is actually separating into bank. Now you can see here, BSR is the 4-bit bank select register. 4-bit plus 8-bit, you get back 12. Can I move on? This is whatever you're learning in this first few things are the most important. If you don't know this, definitely you won't be able to do anything else. So, coming back to this, see that's the reason why I actually skipped this whole part. I went here, so you understand. This 8 bits here, you see, PIC 18 uses 8 bits to specify a data register, which is the F field. This is the F field, right? It only allows 8 bits. So 8 bits can only specify 256 registers. That means 856. With 8 bits you can only access 256 locations. So therefore, what they did, this limitation. This is a limitation, right? This limitation actually forces the PIC to divide data registers into banks. That's what we saw just now, right? That limitation, 8-bit in the instruction, forces us to, not forces us, forces the engineers to divide this into banks. And each bank may have 16 banks. So only one bank can be activated at one time. So if you want to use another bank, you need to move LB that particular bank number. So once you activate this bank will be active until if you change it to another bank. So as long as if you do one, if you want to change, then you have to move LB another bank value. Is it okay? So that's a problem here. The problem is when operating on data register in a different bank switching is needed. Bank switching needed means, like I just mentioned, let's say the first addition operation is performed working register with hex 100. Let's say the second operation you need to do is working register with hex 200. So can you still, you need to switch the bank, right?
Yes.
So what do? You have to move LB 2. Do you get? I think I can erase this part, right? So just now I mentioned we have the first case, let's say the second one you want to do the same thing, but you want to add working register with hex 200 for example. So can you straight away write like this? Where you want the answers to be stored? 5 register or working register? 5. Let's say in actual reality, after you add this one, you want to add with hex 200. I'm not drawing that, is it okay? So if you write the instruction like this, will it be correct? When you do the second one, again it will add to the content of 100. So if you want to add to the file register 200, you need to switch the bank. So you need to add here, you need to change the bank. Move LB to 2. If you don't do this, this is what we know as bank switching. You need to switch the bank. Otherwise, it will refer back 100. Is it okay? So, which means the problem that now we're having is the limitation forces us to divide into banks. So when you divide into banks, we'll have the bank select register to select the bank because the instruction only allows 8. So that means each time you need to select the right bank. Therefore, if you have a lot of, if you want to access different banks, you need to keep switching the bank. So this switching the bank incurs overhead and may cause program errors. Now what do we mean by overhead is that, you see this unnecessary line? This is actually a code, right? This one each time in between you need to add. So it actually adds up, takes up more space. So it's known as taking up, it incurs overhead. And may cause program errors. May cause program errors mean what? Suddenly you're writing a very long program, you forgot to activate the bank. Will you get the right answer? You'll get wrong answer because you just forgot that the one particular bank. So that's the problem.